So today we are going to talk about indirect proofs. So last time we have seen an example of indirect proofs. It is called proof by contraposition. And there is another common method called proof by contradiction. So let me briefly review the idea about these two concepts. So first of all, for proof by contraposition, it is usually we try to prove something like P implies Q, something in this form. But we notice that P implies Q is logically equivalent to not Q implies not P, right? So this is called the contraposition of this one. This is called the contraposition of this one. So they are contraposition of each other. So if you want to prove this, it is the same as if we are proving this. Okay? So this gives us more freedom to choose. If this is easy to prove, we do this. If this is difficult, we may try to convert this into this logical equivalence and then try to prove this. So if you try to prove this, then you can now use direct proof method by assuming that not Q is true and then get the conclusion that not P is true. Is that okay? So you do the conversion, and then once you get this, you can do whatever thing you want, even if you want to prove this by using a direct proof method. Okay, so this is the first type of indirect proof. Now the next one is proof by contradiction. Now contradiction is general. You can think of this as, I have a certain statement P. Whatever P it is, P can be a very complicated compound statement. Like in this form, P implies Q. It is still okay. Just a general P, any statement P. We want to prove a statement P. We actually see that this is equivalent to proving true implies P. These two are always having the same truth value. Is it okay? Because when P is true, T implies P will be true. If P is false, T implies P will be false. So if you prove this, it is the same as if you are proving this because they are two the same. Okay? But now, this doesn't give you anything new. So if P is already difficult to prove, then T implies P should still be difficult to prove. But on the other hand, T implies P is equivalent to its contraposition. The contraposition of T implies P will be what? Not P implies false. Okay, so what does it mean? It means that if you want to prove P, it is the same as if we are trying to prove not P implies false. And what is the physical meaning of not P implies false? Not P implies false means that if we start with not P, then we should arrive at something that is always false. So if I want to prove something that is true, like the sun rises in the east, then maybe you may try to prove that. What if the sun does not rise in the east? Then somehow, if you start with this assumption and then you will say that, okay, if the sun does not rise in the east, then blah, 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 blah will happen. And this can never occur. Then you arrive at something that is called a contradiction, always false. And then you actually prove that the original statement is correct. Is that okay? So we will take a look at this example soon. But these two are, you can see that they are actually closely related. Because here, these two are actually contraposition of each other. So contradiction is a special case of proof by contraposition. You can think of this like this. So this is a theorem. Okay, we have proven last time. If 3n plus 2 is an odd integer, and assuming that this n represents a certain integer, then n has to be odd. This is what we have discussed last time. And then let's review the proof that we have done. So we prove this by contraposition. So this is a statement P that we have. This is the statement P. And this is the statement Q that we have. Is that okay? So this is a theorem in this form, P implies Q. So instead of proving P implies Q, we are proving not Q implies not P. Is that okay? So we are proving the equivalence. So if you look at the proof first says, suppose that n is even. So we are assuming that not Q is true at the beginning. And hopefully, after a certain step, we will get the conclusion of not P. So let's take a look of what follows. So then we will have because n is even, so n is equal to 2 times k for some integer k. Okay? Even. Now, because n is equal to 2k, so 3n plus 2 will be equal to what? It will be equal to 6k plus 2. And now 6k plus 2, you can take away a factor of 2 outside. It is 2 times 3k plus 1, right? And then it is 2 times an integer, so it is an even number. Is that okay? So here, if you look at this, this part is not q. And in the end, we will have 3n plus 2 is even. This is not p. Is that okay? So at this moment, we have actually started with not q and arrive at the conclusion of not p. So we have actually showing, we've now shown that not q implies not p. So we can conclude that this theorem is correct because by contraposition. Okay? Okay, now this is the first proof. Okay, we now try to prove this again, but using proof by contradiction. So let me copy it again. So this is the theorem that we have. If 3n plus 2 is odd, then n is odd. Okay, and we are now proving this again with a different way. Okay, if we start by proving with contradiction, so what should we do? So here, we look at everything here, everything here as a statement P. This is a statement P. So we first assume that P is wrong. So assume that the theorem, or this statement, the theorem, is false. It is wrong. And what we shall do, so this is assuming that this is false. We start with not P. And hopefully, after certain steps, we will get something like a contradiction in the end. We will arrive at some contradiction as a conclusion in the end. If we arrive at certain contradiction as a conclusion at the end, then we are actually showing not P implies false. Okay, if we have not P implies false, then we have P has to be correct. Is that okay? So this is the strategy that we have. Okay, so let's fill in the blanks. So we have nothing here. So let's try to do that. So assume that this is false. So what is meant by the theorem is false? So this is a conditional statement. If something, then something. If this is false, then what does that mean? When can this be false? If something, then something. When can this be false? There is only one case. So this is like if A then B, right? A implies B. So it is false only when A is true and B is false, right? Okay, so if we start with this assumption, assume the theorem is false, then we have what? And then we will have 3n plus 2, it is odd, and n is not odd, n is even. Is that okay? So far, so good, right? So this is the only case that this is not true. The only case if something, then something not true is when the first part is true and the next part is false. This is the only case. So if we assume that this is false, that means that we have this. Is that okay? Now, let's try to get a contradiction. But getting a contradiction could be messy. So we have to be clear which sentence we are using. So here, let me write down. So I'm going to use this fact, n is even, to help us. since n is even, it means that so n is equal to 2k for some integer k. Is that okay? Is that okay? Now n is equal to 2k for some integer k. So we have so again. 3n plus 2 is equal to 6k plus 2 is equal to 2 times 3k plus 1, and then it is equal to even. Is that okay? And now we get a contradiction. Where is the contradiction? Contradiction must be something that you have always false, right? So where is the contradiction? 3n plus 2 is equal to even. Is it a contradiction? Well, this is just, I'm saying that 3n plus 2 is even. So nothing wrong. It could be even, right? The contradiction actually occurs when we have this sentence, 3n plus 2 is equal to odd. This is something like a premise or a mini conclusion starting from this part. And then we have another mini conclusion, 3n plus 2 is even from this part. Is that okay? So if you still remember, we have some steps and reason. So this is some sentence we have obtained earlier. This has some sentence we have obtained later. So let's call this sentence A, and let's call this sentence B. When we have A, when we have B, then we should have A and B, right? But now A and B is false. False. So in that case, we arrive, this is the contradiction that we arrive. At the same time, we are saying 3n plus 2 is odd. And at the same time, we are saying 3n plus 2 is even. And this is impossible. So 3n plus 2 cannot be both odd and cannot be both even. Is that okay? So this is the contradiction that we have. Okay, so you can mark this as A and B. The sentence A and B gives us a contradiction, or you can simply say contradiction occurs. So once you have this one, you can say the theorem is thus true. Then this is the end. This is a proof. Okay, so let me briefly review again. So we start with not P, and then we get a contradiction. Not P implies a contradiction only occurs when you have the first assumption has to be wrong. So if the first assumption is wrong, that means that the theorem is false is wrong. The theorem is false is wrong. It means that the theorem originally has to be correct. Is that okay? Okay. Now this is an example. Okay, but for the purpose of proof by contradiction, you just need any statement. You do not need to have something like P implies Q to start with. So let us take a look of a very old result that is known by Euclid a long time ago. Okay. Okay. So first of all, let me define a concept called rational number. So what are rational numbers? So rational numbers are numbers that can be expressed as a ratio of two integers. Okay. So for instance, 1 over 2, this is rational because it is 1 and 2. Okay. 0 is rational. 0 is 0 over 1 or 0 over 5. It is rational. Is that okay? 0.51267. This is rational. So why is it rational? This is equal to what? 51267 divided by 100000. This is rational. Is that okay? 0.333. This is also rational because this is the same as 1 over 3. Okay? Is that okay? So as long as a number, okay, even it need not be always less than 1, minus 75.2, it is also rational. Is that okay? So it's just like minus 752 divided by 10. Is that okay? As long as it is a ratio of two integers. The bottom part cannot be 0, of course. Okay. If it is a ratio between two integers, then it is a rational numbers. Otherwise, a number is called irrational. So a long time ago, people are interested. So because long time ago, people they use rulers or compass to build houses, to draw figures, right? Usually they want to have ratios so that you can draw this and then you can draw that, and then it's perfect. It is good if everything can be measured as a certain ratio, integral ratio of two things. But then, if you look at a square, so if it is a square, this is a square. Let's say this is of length 1, this is of length 1. Then the diagonal will have square root 2 as its length, right? This is by the Pythagoras theorem. Yeah. And then it turns out that no matter how you do this ratio, there is no way to express that square root 2 as a ratio of two integers. Okay, in fact, we are now going to show that square root 2 is an irrational number. Okay, so how do we show? So square root 2 is irrational. So how do we show? So of course, the first thing that we should get in our mind is, can we do this with a direct proof? Because direct proofs are usually very easy. But what is meant by direct proof? Square root 2 is not rational. If a direct proof, then we will need to say that, okay, if I get an integer of this one and integer of this one, then the ratio cannot be equal to square root 2. But in that case, there are many choice of the integers that we need to check. There are infinite choice, and then we don't have time to check it one by one. We check it is not equal to 1 over 2. We check it is not equal to 1 over 3, and so on and so forth. But it still doesn't mean that there is still some integers around that we cannot use to make it a over b equals to square root 2. Okay, so do you understand my point? So if I want to get a direct proof, then I have to check all pairs of integers. All pairs of integers means that we are going to run out of our lives to check. So now let's try to prove it with an indirect proof. Let's prove it by contradiction. So the theorem that we want to write down is square root 2 is irrational or is not rational. Okay, so this is a statement P that we are going to show. This is a statement P that we are going to show. So we first start with assume that the theorem is false. So what does it mean? So I can save some. This is a very simple statement, a simple theorem. So we just assume that this is wrong by assuming that square root 2 is rational. Is that okay? Okay. And hopefully, after a certain step, we get a contradiction. Okay, this is our idea. Okay, now, so nothing that we can do directly here. So let's do this step by step. So if we assume that square root 2 is rational, then what can we write down next? What is meant by rational? Rational means what? Okay, P over Q. Very good. It is a ratio of two integers, right? So if this is okay, this is true, then square root 2 can really be written down as a ratio of two integers, P over Q, for some integers P and Q. Is that okay? Now at this point, so there are if there are so there can be many choice, right? There can be many choice. If P over Q is okay, then 2P over 2Q still gives the same ratio. So in that sense, let us make this PQ more special. So we can find PQ, but once we find PQ, we make PQ even more special. So that okay, so what we are going to do is we then cancel. So we are going to cancel the common factor so let's say common factor of PQ, and let's say we make it into so we make them into P prime, Q prime, so that square root 2 is equal to P prime over Q prime, and these two, they don't have any common factor. So let me write down. Is that okay? So what we are going to do is, so if square root 2 is really a rational number, then you can express this as P and P over Q. But then we try to make this PQ even more special. So if there are still common factor between this P and Q, we remove it. So we divide the common factor on the top and at the bottom at the same time. So the P becomes smaller, Q becomes smaller. But then they do not have any common factor. You understand my point? So for instance, suppose that someone magically tell me that square root 2 is equal to 12 over 20. I don't know why this is correct, but let's say 12 over 20. Then we find out what is the common factor between 12 and 20. So maybe it is 4. So we take out 4 from both parts, so we make it into 3 over 5. Is that okay? So once we remove the common factors, then they don't have any common factors anymore. Is that okay? Okay, so now, so we start with square root 2 is equal to something over something, but these two things does not have any common factor to begin with. Okay?